In the modeling and simulation course, we dive into creating models that simulate the thrilling journey of falling objects. Imagine calculating the exact moment an object will hit the ground when dropped from dizzying heights. To get these spot-on predictions, we need to consider all the forces at play, among which gravity, drag, and sometimes even buoyancy. The type of flow around the object, whether it's a calm laminar flow or a wild turbulent one, is key. In this video, we'll show you the fascinating differences in how objects tumble through gases and liquids. Get ready for a fun and informative exploration of falling objects.
This video explores the fascinating dynamics of objects falling through the air. Typically, the flow around these objects is turbulent, creating drag forces that influence their descent. Let's dive in. Here, we have an exhilarating skydiving scene from the towering heights of Dubai. Initially, the skydiver experiences free fall until the parachute deploys. In this thrilling descent, both gravity and air friction come into play. The faster the fall, the stronger the drag force becomes. Two forces come into play here. The drag force, which always opposes the falling speed, is directed upwards, while gravity pulls downward. At a certain point, the falling speed is increased to the extent that the drag force balances with gravity, halting further acceleration and stabilizing the speed. When the parachute opens, the drag force dramatically increases, guaranteeing a safe landing.
Turbulent flows are inherently chaotic, and they come into play when an object's speed through the air is sufficiently high. As mentioned earlier, the faster the fall, the greater the drag force. This force, as shown in the formula, increases quadratically with speed. Here, ρ represents the air density, but the falling medium could also be water. The drag coefficient tells us how streamlined the object is. A streamlined object has a low value of CD, while for a blunt object the opposite applies. The frontal area is represented by AF. For a falling sphere, this area is that of the circular mid-section of the sphere. We'll use this formula later to create equations of motion that describe the object's fall. What we have just discussed applies also to a girl doing a bungee jump. Let's take a look.
This girl is falling while attached to a bungee cord. Therefore, there is an additional force present related to the elongation of the cord. The greater the elongation, the greater the opposing elastic force. There is also a turbulent drag force that opposes the speed. The previously discussed formula applies to this force. Gravity is constantly pulling downward. When the girl shoots upwards, the bungee cord is still stretched, and the elastic force is still at work. Since the speed is directed upwards, the turbulent drag force now works downwards. Gravity remains unchanged. At this point, the bungee cord is no longer stretched. Moreover, the cord cannot withstand compressive forces, so from this moment, only the turbulent drag force and gravity are at work. Here, you see a bungee jump from the Macau Tower. I included this video because it perfectly shows the straight line motion of someone jumping from that incredibly tall tower. You can see him falling down as a tiny figure. Soon, he's out of sight for a moment, and then he shoots back up under the influence of the elastic bungee jump cord. And there he goes. Here you see indoor skydiving in action. Besides gravity, the man experiences an upward force from the air blasting over him from below at high speed. This force is essentially turbulent drag. When the man adopts a streamlined position in the air, as you can see here, the drag coefficient is low. The frontal area is also minimized, matching the elliptical cross-section of his body at the hips or shoulders. This combination allows the man to control the skydiving experience. Something special is happening here because the man is moving through the air, which itself is also flowing. This creates a relative speed between the man and the air. It's this relative speed that generates the turbulent drag force, making the whole experience more dynamic and thrilling. This is not a streamlined position, and the turbulent drag coefficient is high. The frontal area is also larger than before and consists of the man's torso, head, and spread arms and legs. This will result in a large drag force, which propels the man quickly upward. In summary, there's a fascinating interplay between gravity and turbulent drag force influenced by the man's position in the airflow and his speed relative to the air. This dynamic makes skydiving a thrilling and exhilarating activity.
So far, we've shown examples of objects being swept through turbulent airflow. But when the falling speed is low, the flow around the object becomes laminar. This type of flow is much calmer and less chaotic, characterized by the absence of velocity fluctuations and vortices. As a result, the formula for turbulent drag force needs to be swapped out for Stokes' law, which tells us that the force is proportional to the speed rather than the square of the speed. When an object falls in a liquid instead of air, buoyancy quickly comes into play. The combination of gravity, buoyancy, and laminar drag force determines the object's motion. This makes for a much smoother, yet equally fascinating, descent.
Here you see a glass tube filled with liquid. Inside, a small ball is falling. Right now, the ball isn't visible, but it will appear any moment. The ball is falling due to gravity, but this is countered by buoyancy and the laminar drag force. You'll notice Stokes' law, which includes the dynamic viscosity of the liquid and the radius of the ball. The ball's speed is now stabilized because gravity, buoyancy, and drag force are perfectly balanced. With no extra force to accelerate it further, the ball falls at a constant speed. Watch closely as it gracefully descends through the liquid.
The motion of falling objects in air or liquids can sometimes be very complex, especially in turbulent flows. Think back to skydiving, where a person's acceleration and speed exhibit fascinatingly complex behavior, both changing dramatically over time. In some cases, however, an object's acceleration is constant. Like when it falls in a vacuum. Here, the object's acceleration is exactly equal to the acceleration due to gravity, whether it's heavy or light. This fact often defies our intuition. In the upcoming video, you'll see a feather and a ball falling through the air. With air resistance present, the feather, as expected, takes much longer to reach the ground. But then, we remove the air from the setup and repeat the experiment. Will the feather and the ball hit the ground simultaneously? It's a surprising result that you won't want to miss.
We find ourselves in a massive vacuum chamber. Right now, there is still air in the chamber, but soon it will be completely removed. The goal of this experiment is to demonstrate that in a vacuum, all objects, whether heavy or light, fall at the same speed and hit the ground simultaneously when dropped from the same height. Get ready to witness a fascinating display of physics in action. This aligns with our everyday expectations. The ball falls faster than the feather. The reason for this is the presence of a drag force, which impacts the feather more than the ball. Initially, both the ball and the feather accelerate. However, the feather quickly reaches its terminal velocity as the drag force balances out gravity. At that point, the feather stops accelerating. According to the formula, the terminal velocity is low, because the feather has a small mass. The ball, on the other hand, continues to fall faster and likely hasn't reached its terminal velocity yet. This difference in behavior showcases the fascinating effects of drag and mass on falling objects. The air in the vacuum chamber has now been removed and the experiment is being repeated. This time, however, there is no drag force present. You can see that the ball and the feather fall at exactly the same speed and hit the ground at the same time. In this situation, only gravity is at work, which means that both the feather and the ball experience an acceleration equal to the acceleration due to gravity. Constant acceleration results in a linear increase in speed. The position follows the parabolic relationship characteristic of uniformly accelerated motion. Here is the proof that heavy and light objects in a vacuum fall at the same rate and hit the ground simultaneously.